So today I will tell you about how to cook a quark gluon soup with supercomputers. So first I would introduce the ingredients, the quarks and gluons, and then introduce the soup and how they are created or in the experiments. And then I will tell you how to cook this soup from the fundamental theory, which is quantum chromodynamics. So to do that, I will introduce the recipe, which is Lattice QCD, the technique that we will use. And then I will introduce you to some of our super kitchens with which we cook the soup, like the supercomputers. And then I will briefly touch upon how the soup tastes, or what are the properties of these soups, and how can we infer them together with experiment, some modeling, and the theory itself. So let's start at the very beginning. So nearly all the visible matter that we see in the universe consists of atoms. The atoms has a size which is of the order of 10 to the minus 10 meters. So compared to the human hair, which has a diameter of the order of 10 to the minus 5 meter, which means a fraction of 1 followed by 5 zeros. So an atom is 100,000 times smaller than a human hair. And the atom consists of a core known as a nucleus. The nucleus itself is 10,000 times smaller than the size of the atoms. And it is circled by the electron, which is elementary point particles. The nucleus consists of bound states, protons, and neutrons. The masses of these protons and neutrons are of the order of 10 to the power minus 27 kg. Compared to an average weight of an average human cell, which is 1 fraction of a trillionth kg. So this mass of a neutron and protons are 100 billion smaller than a weight of a human cell. And compared to the neutron and proton, the masses of electrons are at least 1,000 times smaller. So the mass of the entire universe that we see today is essentially concentrated on these neutrons and protons, which are known together as the nucleons. So these nucleons are not elementary objects. They consist of quarks, and these quarks are bound together with another together through another particle called gluons. The forces between these quarks and gluons are very strong. I will sort of briefly give you a feel how strong this force is. And the theory that describes this strong force of nature is called the quantum chromodynamics. Bound states of quarks are known as hadrons. So usually they come in two types of varieties: bound states of 3 quarks and bound states of 2 quarks. So bound states of 3 quarks are known as baryons. And with each baryon, you associate a number, just the counting number of a baryon of +1. So if you have 2 baryons in the system, you have baryon number 2. Since the baryon is composed of 3 quarks, the baryon number associated with the quark is 1/3. And then each of them has an antiparticle, which means it has the same mass as the baryon, but carries an opposite baryon number and opposite electric charge. So a baryon number of an antibaryon is -1, and if you have a system with a baryon and an antibaryon, the total baryon number of the system would be 0. These antibaryons consist of 3 antiquarks, and then the baryon number of the antiquarks are thus -1/3. Then the other type of bound states are mesons, which are bound states of quarks and antiquarks. Since they are bound states of quarks and antiquarks, they carry a baryon number of 0. So that baryon number adds up, but what doesn't add up is the mass. So if you look at the mass of a proton, this is nearly mass of 300 quarks. So almost the entire mass of the proton, which is 10 to the minus 27 kilogram, concentrated in a size within 10 to the power minus 15 meter, is generated through the strong force amongst these quarks and gluons. So if you take this mass and try to convert it energy and try to figure out the force amongst these quarks, then what you will end up is the force between these quarks is 10 to the power 5 Newton, or in more direct feeling, it means it's equivalent to the force of 5 elephant, of the force given by the Earth on 5 elephant at the surface of the Earth. But what happens if you try to push these quarks or these elephants in a very violent manner and can we try to free them up from inside these nucleons? So the way to give this violent push is to increase the temperature of the system. So you give higher and higher thermal jitters. And if you crank up the temperature to 1 trillion degrees Celsius, of the order of 1 trillion degrees Celsius, then then the quarks and gluons do not remain confined within the nucleus. And what you end up is a new state of matter, a quark-gluon soup. So this state of matter is known as the quark-gluon plasma. So if we look back at the history of the universe and follow the evolution of the universe, then we can try to guess at what point of the evolution of this universe such high temperature could have existed. And so at that point of time, the universe was consist of quark-gluon plasma. So just after the Big Bang, when the universe started, so after a very short period, after 10 to the power minus, of the order of 10 to the power minus 37 seconds, the universe consists of quark gluons and all other elementary particles. But at this stage, the quarks themselves were massless. So at a time when the temperature was 10 to the 15 Kelvin, after 10 to the power minus 10 seconds, the quarks becomes massive, and at this point, quarks and gluons form the prevailing matter in the universe. So after 10 to the power 5 seconds, or microseconds after Big Bang, when the temperature is of the order of 1 trillion Kelvin, then these quarks get bound together in form of hadrons. And then as time progresses, and 100 seconds after the Big Bang, then this nucleons come together and in the form of ions. And then after 3 times 10 to the power 5 years, these nucleons and these ions and electrons combine to form atoms. And then of the order of 1 billion years after the Big Bang, the structure starts forming, and almost nearly 14 billion years after the Big Bang, here we are today. So if we look back in the history of the universe, so nearly after a microsecond after the Big Bang, the temperature was of the order of 1 trillion degrees Celsius. So this trillion degrees Celsius means, just to give you a feeling, this is 70,000 times hotter than the center of the sun. And at those times, we could expect that such a quark-gluon soup existed in the universe. Of course, we cannot recreate a Big Bang or the universe itself, but in order to recreate this quark-gluon soup on Earth, what we can do is we can do little bangs. So we can collide fast-moving heavy nuclei, moving almost nearly at the speed of light, and these nuclei are heavy, typically gold or lead, and they collide on each other, and after this collision, we expect a quark-gluon plasma is formed, and then this quark-gluon plasma expands, and as it expands, it cools, and as it cools, then again, quarks forms their brown states, and then at this point, we observe them in the experiment. And looking at this, we try to infer whether a quark-gluon plasma was formed in such little bang experiments. There are mostly two types of this, two of these atom smasher currently working in this world. One is obviously our own relativistic heavy ion collider at the Brookhaven National Laboratory. And here there are currently 2 working experiments, the Phoenix and the Star. They are almost entirely dedicated to study the properties of this quark-gluon soup. The other atom smasher is located in CERN Geneva, the Large Hadron Collider. In this collider, the ALICE experiment is entirely dedicated in studying the properties of this quark-gluon soups. And the other experiments like ATLAS, LHCb, and CMS, they also do something, but they're not dedicated experiments for this, for quark-gluon plasma studies. So by looking at the light, the frequency distributions of the light emitted from these collisions, one can estimate the temperatures or the average temperatures created during these collisions at RHIC and LHC. So when experimentalists do that, what they found that the average temperature that has been reached in RHIC is of the order of, it's approximately 220 MeV or 4 trillion degrees Celsius, which is 270,000 times hotter than the center of the sun. For LHC, the average temperature reached is even higher. This is of the approximately 300 MeV or 5.5 trillion degrees Celsius, which in other terms is 70 times hotter than the center of the sun. So this we can estimate from experiments, but the question remains, are these temperatures high enough to recreate the primordial quark-gluon soup? To answer this question, we have to really go back to our fundamental ingredients, the quarks and gluons, and go back to their fundamental interactions and try to calculate at what temperature such a quark-gluon plasma or quark-gluon soup can be formed. To do so, what we do is we take the QCD theory, the theory which describes the interactions between these fundamental particles, and then we take the theory, discretized it in space-time grid, and put a quark at every grid point, and put a gluon in the connecting link between the two grid points. And amongst them, the quarks and gluons interact according to the theory of their fundamental interactions from QCD. So this is an approximation-free and completely parameter-free calculation starting from the fundamental theory of the quarks and gluons. Why is this calculation so difficult? So just to give you an idea, if you take a box, which is roughly 3 to 4 times larger than the size of a proton, and 64 grid points in each of the x, y, z, and time directions. So if you consider such a box, modest box, which is for practical calculation, then the number of variables that enters in this calculations is of the order of 1 billion. So obviously, we cannot solve this theory in our day-to-day laptops. So we need a super kitchen to cook this soup. So our super kitchens are the supercomputers. Here is an example, the Titan supercomputer at the Oak Ridge National Laboratory. And typically, these supercomputers are at least 1 million times faster than our day-to-day laptop that we use. And it's only the supercomputers are not enough. You need to stack our kitchens with very, very state-of-the-art utensils. So you need very high performance code to get utilize the full power of these super machines. Here I give you a few examples of the supercomputers that we actually use in our calculation, I will be a sample of which I will be showing later. So this is the rank 1, world's fastest supercomputer at present in China, the Tianhe 2. The next fastest, the Titan in USA, in Oak Ridge National Lab. Then the third fastest, Sequoia in Lawrence Livermore National Laboratory. Then the Mira, the 5th fastest in Argonne National Lab. The world's 8th fastest computer, Juquin, in Jülich, Germany. And the ranked 9th is the Vulcan in Lawrence Livermore National Laboratory in USA. So all these computers, the supercomputers, we use to get our results, and these results will be shown later on in this talk. Now, once we have our recipe and the kitchen, then really us, the theorists, we come in and try to say what really we have to do to get or understand or calculate the temperature need to cook the soup. We have to find proper observables. So again, I refer back to what I said before. For each baryons and antibaryons carry baryon number +1 and -1. And the quarks and antiquarks carry fractional baryon number of 1/3 and -1/3. So if we can measure a quantity which is b squared, like the fluctuations of the baryon numbers, then if the system consists dominantly of baryons, then this quantity, the fluctuations of baryon number would be 1. And if the system consists dominantly of quarks and antiquarks, then the fluctuations of this baryon number would be 1/9. So we can go and try to find a measure of this quantity. So here in this plot, what I show is such a measure of this quantity as a function of temperature. Here it's given in MeV. And what you show, this measure of this baryon number squared changes as you increase the temperature. It changes from 1 and goes over to 1/9, which tells us that at this point, at these temperatures below, the system is dominantly consists of baryons and antibaryons, and at these temperatures, the system consists of quarks. And this change happens gradually. And at this point, around 155 MeV, what we can see that this starts deviating from 1, and so the fractionally charged fractional baryon number starts to appear. And at this temperature, we know this temperature where it happens, the quark gluon soup is being created, and this temperature is roughly approximately 2.8 trillion degrees Celsius, or 190,000 times hotter than the center of sun. So compared to that, here is REEC, the average temperature estimated at REEC, and here is at LHC. So by performing this calculation, we know and we can ensure that this quark gluon soup or quark gluon plasma has been created in REEC and LHC. We can do this in this thing, and we have looked into this and did these things in many, many different observables and many, many cases, and here is a list of those things. And in each case, we found, I gave you a simple example, but there are other complicated things, and each case we found that this is the transition temperature, the temperature that we need to cook this quark gluon soup. I said before that we need to collide this nuclei and dump a large amount of energy to create this quark gluon soup. So what is the energy density that is critical energy density that is required to calculate, to form this quark gluon soup? So we can calculate the energy density of QCD matter, which has been done here, and we can calculate as a function of temperature the energy density and see what is the energy density in the temperature region where the transition happens. So if you go and check and try to do it in more accessible units, then what we find, the energy density that is needed to form this quark gluon soup is approximately 5 times 10 to the power 34 joules per meter cube. So still, this is not a number that you can conceive very easily. So imagine the total energy of the sun, not the energy that is reaching Earth, the total energy of the sun that the sun is emitting over a year. Multiply it by a factor 4, and then squeeze that whole energy in a box with each side of 1 meter. So that is the energy density that is needed to form this quark gluon soup. And the only way we know that is to perform these calculations by going through supercomputers and doing these calculations from the fundamental theory. I've said that once the quark gluon plasma is created in experiments, it expands and it cools down. As it expands, it flows. It flows like water. It flows. So the flow of this soup can be described following the principle of how the water flows, or the hydrodynamics. But the imperfection of this fluid, how this fluid flows, is determined by what is the resistance that the fluid provides as it flows. And that fluid imperfection is characterized by a quantity, which is the shear viscosity eta divided by temperature times energy density and pressure, plus pressure. So here is shown this measure of the fluid imperfection for various different quantities over a large range of temperature from of the order of microkelvin to trillion Kelvin. These are quantities for which we know that the resistance that it provides during the flow is small. So this is ultra-cold atoms here. This is helium-1. This is water. And this is the estimated imperfection for quark-gluon plasma. This is shown in a unit of 4 pi. So in the unit of 4 pi, this is 1. And this is sort of the conjectured minimum value of this fluid imperfection that you can achieve in any quantum theory. So this shows that the quark-gluon plasma that is created in the experiments is a nearly perfect fluid. It almost doesn't provide any resistance as it flows, and the resistance it provides is the minimal that you, almost close to the minimal that you can have. How did we come to this conclusion? To come to this conclusion, this fluid imperfection measure, what you need, obviously, the experimental measurements. And then you take the experimental measurements and model with the hydrodynamics, the principle by which water flows, which is nothing but energy momentum conservation locally. But in order to obtain this, what you also need is the really theory input, that's the microscopic properties of the quark-gluon soup. So these microscopic properties of the quark-gluon soup comes from the theory which is calculated from Lattice QCD, such as how the energy density or the pressure changes as a function of temperature. I have already shown you, given you a feel how the energy density changes as a function of temperature. Let me give you a feel of how what's the pressure inside the soup. Here is the pressure as a function of temperature, and this is the estimated average temperature for a week, and this is LHC. So if I convert it into our more understandable units, at LHC, the pressure inside the soup is 10 to the power 30 bar. Remember, the pressure at the sea level, at the surface of the Earth, is of the order of just 1 bar. And if you go to the core of the Earth, the pressure inside the core of the Earth is few billion bar. So the pressure inside the quark-gluon soup that is created at RIC is trillion times larger than the pressure at the core of the Earth. Let me go on to a slightly different topic, and we try to infer what happens if you change the balance of the ingredients a bit. So we papered the soup by adding a little bit more quarks over the anti-quarks. We add more quarks over the anti-quarks. And then since the quarks carry a baryon number, what we are essentially doing is we are adding some baryon density to the soup. So now we have another axis, apart from temperature, the baryon density and the temperature. And what we would try to figure out or try to look is this, how the transition between our normal hadronic matter to the quark-gluon soup happens as a function of both temperature and baryon density. So such a plot or such type of plot is known as a phase diagram. So for small values of baryon density, we know, as we have seen, this is a smooth and gradual crossover from the hadronic world to the quark-gluon plasma soup. Just like the melting of butter, it happens at a smooth and gradually. This we know and has been established from QCD lattice QCD calculations. For large baryon density, what we expect, we don't know yet, what we expect from various model-based studies, that there could be a region where the quark-gluon soup and the hadrons can coexist together. Just like if you boil water, then the water vapor and the liquid water can coexist together with each other. So this is known as the first order transition where the coexistence of two phases are possible. The point where this coexistence ends and it goes over to a smooth crossover is known as the QCD critical point. Just in the case of water, we know where this QCD critical point is and where this coexistence phase is. So this is in the case of water. So if you are at 100 degrees Celsius, the water starts boiling, and at that point, you can have a coexistence of water vapor and liquid water. But if you crank up the temperature and go to higher density, like 10 to the power 22 molecules or water molecules per centimeter cubed, and crank up the temperature to 374 degrees Celsius, then above that, even in water, this coexistence phase starts to stop existing, and then you can have a smooth crossover between water vapor and liquid. So of course, our our goal is to draw such a phase diagram for the fundamental quark-gluon matter similar to that of water. We would like to know where this coexistence phase is. We'd like to know where this critical point is for the fundamental matter, just like what we know in water. How can we do that? In experiments, the way we do that is we can collide nuclei with varying energies. So as we go to smaller and smaller energy, the more and more incoming baryon stops here, and that increases the baryon density inside the quark-gluon plasma. So smaller and smaller, going back to smaller and smaller energy, collision energies in RHIC, this program is known as the energy scan, the beam energy scan at RHIC. So we go to smaller and smaller energies, and once we go to the smaller and smaller colliding energy, I can probe a quark-gluon soup with more quarks than anti-quarks. But to know the phase diagram, what we have to chart the phase diagram, just like in the case of water, what we need to know how this collision energy connects to the thermodynamic observable that we plot along the phase diagram, like the temperature or the baryon density. To do this translation, it is easier to trade the baryon density in terms of the energy needed to add an additional baryon to the system. This energy is known as the baryon chemical potential. So it is easier to trade the baryon density in terms of the baryon chemical potential. And this baryon density and baryon chemical potential has one-to-one correspondence. I will show you one example that once you know the baryon chemical potential, you can go back to the baryon density or the other way around. So once we do this trade-off, then to chart the phase diagram, what we have to do is to do a map or write down or find a relation between the collisional energy, which is the only tunable parameter in the experiments, and the thermodynamic variables like temperature and chemical potential. So how can we do that? So we have to choose, at least since we need to determine two variables, we have to choose at least two appropriate quantities. This has to be carefully chosen from both sides. So these two quantities are measured in experiments as a function of the beam energy. And these quantities, the same quantities has to be calculated in the theory side as a function of temperature and the baryon chemical potential. So then we can match theory and experiments and do a mapping between this collision energy and the thermodynamic variable. The only one issue here is the experiments. In experiments, what we observe, as I said, is mostly what we observe is when the bound states of quarks are reformed at this stage when we observe in the experiment. So this stage of the collision is known as the freeze-out stage. So essentially, when I compare an experimental observable and a theory calculation, so what we will essentially map is the collisional energy and the thermodynamic variables T and mu B describing this freeze-out stage. So how can I construct these two observables? To do so, what we came up and what we suggested before is the cumulance of net charge fluctuations. So what is that? So you measure the net charge, which is the number of positive charges minus number of negative charges in each of the collision. Once you measure that, then you can do a distribution, a histogram distribution. So what you can look at is the number of collisions in which net charge of delta NQ has been measured as a function of delta NQ. So just a histogram. Then what we do is to characterize this distribution, or in other words, calculate various cumulants which characterizes this distribution, such as the mean, variance, and skewness. Here is an example of this distribution of net charge here, and number of collisions where with delta NQ has been measured from the Phoenix experiment. So what are the cumulants? The mean of a cumulant is simply the average value of these distributions, like this. This characterizes the average value of the distribution. The variance characterizes the width of the distribution. Larger the width of the distribution, larger is the variance. The skewness essentially characterizes the asymmetry of the distribution. So if a distribution is completely symmetric around its mean value, then its skewness is 0. If the distribution has a longer tail for values larger than the mean value, then it has a positive skewness. And if a distribution has a longer tail for values which is smaller than the mean value, then it has a negative skewness. So these various cumulants, these various characterizations of this distribution can be measured in experiments and can be also measured in theory. In both cases, it is very difficult. So to do so in experiments, you need millions and millions of events. And to do so in theory, you not only need a large number of large computing time, but you also need very more innovative approach to calculating these things and further improvements in formalisms. But we can do that. And once we can do that, so we can find proper clever observables which are largely sensitive to the temperature or largely sensitive to the baryon chemical potential. So here is an observable which is largely sensitive to the temperature only. This I quote as our thermometer. So this observable is skewness times variance cubed divided by the mean. So this is the lattice QCD calculations of these observables as a function of temperature for various different values of the baryon chemical potential. And with that, I can compare an experimental measurements. Just for example, I take the Phoenix experimental measurements from the Phoenix experiments at a collision energy of 62 GeV. So once you compare the theoretical calculations and overlay the experimental measurements on this blue patch, from that you can infer what is the temperature at corresponding to this collision energy. And for this particular case, it turns out somewhere close to 155 MeV, 160 MeV. So once you know the temperature, you can look at the other one of the other variable, which is largely insensitive to the temperature, but more sensitive to the baryon chemical potential, which I quote as a baryometer, like the mean by variance squared. So here is the lattice QCD calculations of this baryometer at this given temperature. And on top of it, you can, as a function of the baryon chemical potential, and on top of it, you can overlay the experimental measurements. This time, I show the measurements from the STAR collaboration. And you can see by comparing the theory and the experimental calculations, from there, you can read off the chemical potential associated with each of these collisional energy. The only thing I should say is probably it's good to mention that we constructed and calculated these observables or these quantities almost a few years before when the experiments came up, experimental results came up. So after experimental results came out, both from STAR and experiments, then we could do this type of comparisons and do this mapping between the energy, collisional energy, and the thermodynamic observables. As I promised that one can make a one-to-one correspondence between the baryon density and the chemical potential. So once I know the chemical potential here, I can calculate the baryon density at the freeze-out stage where we observe as for a given, for different collision energy. So this is the calculations, lattice QCD calculation for the baryon density at the freeze-out for different collisional energy corresponding to RIC. So here is RIC collision at 19.6 GeV. So the baryon density here is net baryon density, the baryon minus antibaryon density, is of the order of 10 to the power 43 net baryons per meter cubed. So how large is this? So if I take a dense object like a diamond, so the molecular number density for diamond is roughly 1.8 times 10 to the 29. So the net baryon density for a 19 GeV collision at RIC is roughly 100 trillion times larger than the molecular density of diamond. So now, once we know this relation between the, really know the coordinates, quantitatively the coordinates of the temperature and baryon chemical potential, then we can look at or try to put some points in this phase diagram of the quark-gluon matter. So here is the part we know. This is sort of up to roughly up to 19 GeV collisions at RIC. So here are the region that we can quantitatively know in the QCD phase diagram in the temperature and baryon chemical potential phase that we can extract from lattice QCD and experiments. But obviously, what our ultimate goal is to know the full phase diagram in a much larger extended region in the baryon chemical potential or baryon number density. So we sort of try to or hope to map out this full phase diagram as far as possible, exactly like the phase diagram of water that we know so well. To find out this or to probe this, characterize the phase diagram of the liquid formed with these fundamental particles in this at least somewhat closer level to the liquid like water, the second phase of the RIC beam energy scan is planned around 2019 to 2020. This is a following up on the very tantalizing hints from the first phase of such a scan, which just concluded a couple of years ago. So this program, experimental program, will probe the QCD phase diagram in this region of the QCD phase diagram. And for that, if we know and if we can do the corresponding lattice QCD calculations, then we can similarly try to map this part of the phase diagram as much as we can. So currently, the reach of this lattice QCD calculations ends at around 19 GeV of the of the collision energy, and this is sort of the planned energy scan region from the second phase of the RIC beam energy scan. So in order to know the phases of this quark-gluon matter, we need to extend this the QCD calculations to the BES2 regime. This is not an easy task. This also needs a lot of computing time and maybe the next generation of supercomputers, and along with other formalism and other conceptual developments. There are other issues which I could not manage to touch upon. So this is just a broad stroke what in the large program, but there are other issues what Lattice QCD can do, and to a large extent has achieved to various degrees. Of course, what we would really want to know from the fundamental theory, what are the viscosities of the quark-gluon soup, how imperfect is the quark-gluon soup itself, starting calculating from the first principle theory. We can address the issue of how the charges are transported, like the electrical conductivity or how the charges are diffused in this soup. We can calculate how the photons are emitted, or what's the rate of the photon emissions or the dilepton emissions. What are the fate of the heavy quark anti-quark bound states, like anti-quark bound states of charm quarks, which are much heavier, or bottom quarks. These are interesting probe of the quark-gluon soup itself. We can understand and tell how these heavy quarks lose energy as it passes through the soup. These are also important for experimental observations. And furthermore, we can also tell many things which of the bound states of the quark of the quarks, the hadrons, at the edge of the quark-gluon transition, when the bound states or the hadrons are heated up to a very high degree and hasn't gone into the quark-gluon phase, what are the properties and how does this hadrons, the bound states itself look like? With that, I come to my summary. I hope in this talk I could have convinced you that in studies of the phases and properties of the fundamental matter made of object quarks and gluons, Lattice QCD is an essential tool. So with experiments and various modelings, you really need the theory inputs to extract physics out of the experimental programs. And Lattice QCD has made a lot of progress over the last few years, and we can try to quantitatively connect from the theory and experiments on these sides. Of course, some help from the modeling and the simulation sides are also needed. So with these three sides, we can hopefully probe the properties of this quark-gluon soup and its phases. But Lattice QCD is one important component for that. Okay, none of this happens in a vacuum, or none of this happens by myself alone. So here are the most crucial things first, my collaborators. So this is the collaborators, so firstly, the Brookhaven lattice gauge theory group, and then a US-wide collaboration, multi-institutional collaboration, the hot QCD collaboration, and then an international collaboration among Brookhaven, the lattice gauge theory groups of Brookhaven National Laboratory, the Bielefeld University in Germany, and Central China Normal University in Wuhan, China. And I hope I have convinced you one of the key components and the essential components in this business is the computing. A lot is needed from here, and we get these things in the US side. Most of the things we get from the US side, from the support of DOE, Office of Science, Advanced Science and Computing Research, the ASCR, through various big competitive proposals like ASCR Leadership Class Computing Challenges, the Insight proposals, and through this we get computing time in leadership class machines such as the Oak Ridge National Laboratory, Argonne National Laboratory, or NERSC. Apart from that, we are using computational resources in Jefferson Lab, Fermilab, and Brookhaven National Laboratory, which are managed by the US Lattice QCD, US QCD, which is a Lattice QCD consortium for the US here. So they manage various computing resources in these labs dedicated to Lattice QCD. Other than that, we have all this research, a large part of it has been made possible because of our collaborators in Lawrence Livermore National Laboratory who helped us with the computing time in a few big machines. And then there is partnership of advanced computing in Europe, or the press. We get some computing time from them in Jülich and in Italy, and also some local cluster time in the Bielefeld University. And lastly, the funding. The whole research program of this, what have been showing or what has been done in my side, has been funded by the Department of Energy Office of Science, mostly Office of Nuclear Physics, and the Nuclear Theory Group. Thank you. Okay, so the question was asked whether in this region of the quark-gluon plasma in the low baryon density phase and above the freezer at this temperature, whether there is a short-range order in this system of the honest answer is to it is we don't know. We don't know. We don't. So far, we haven't characterized the system to that level. We don't know yet. So obviously, there are some really short-range screening interactions that screens the color. So that certainly is, but we haven't. So we know how this at the short ranges the color screening works, and that is quantitatively known. But beyond that, we don't know much. Yes.
Next question is more experimental. You show all these beautiful supercomputers. How much do they cost?
The computers themselves? I have no idea, sorry. I have no idea how much this computer.
What if you didn't mention the one that's down here?
So okay, right now, which is running here is a prototype of a Blue Gene Q machine, which is already 6 years old. But I don't know the actual cost of it. I guess it's protected by, it's a prototype from IBM. I don't know. It's not in my. Oh, certainly experiments. I mean, it's not. No, it's not in probably not in that order. Yeah. Yes.
Showing how lattice QCD takes on blocks of space and time.
Mm-hmm.
You said, I think by way of example, pick the box that's a few times the size of a proton.
Yes.
What is the biggest system you can actually simulate? I mean, could you put a deuteron in a box and actually say, here's how a deuteron holds together by some direct calculation? Or is that too big for what?
No. Okay. So for this is not my specialty. I don't work on those things. But people do put interactions between two nucleons. That you can do, definitely. You can compute the forces between two nucleons or the potential between two nucleons, or how they scatter or how they interact. That you can do. But going beyond two-body is not, so far it has not been done.
So when you're talking about how the quark-gluon plasma behaves in some collision,
Yeah.
taking a chunk of space and time and saying there are quarks and gluons in there, but you're not including nuclear geometry or anything like that. You're saying, here's how a piece of quark-gluon plasma behaves, and then you connect it to modeling or something to say, here's what I would expect in an experiment. Is that?
No, what we do is we start from the quarks and gluons. So if a bound state is formed, it will be formed. we don't put those. So it will be automatically from the fundamental theory. And all the interactions among these various objects are essentially taken care of unless it is a very, very long range and it needs a huge, huge volumes, then we cannot.
You said there have been major advances in the past decade lattice calculation. What fraction of that is due to changes in, say, your algorithms, developments, in how you use lattice versus brute force, what's the balance?
So, okay. So actually, I would add more to it. So roughly, I would say half and half. It comes from your conceptual and algorithmic development, plus that you have to do it for, that comes with the advancement of computers. Plus also what you have to think or have to keep in mind that apart from this, you also have to connect or go to proper study of the proper theory. You have to come up with proper things, proper observables, look at proper properties like this 2-nucleon force or this freeze out. Those are something which goes beyond the algorithms or the computing itself. Yes. Yes. That is a really, so the question was here that whether you can do the whole standard model on the lattice, including the electroweak sector. At present, no. There is a big problem in introducing, I have to go into a little bit, since I have to answer you in a little bit technically. So there is a big, so it's not yet really clear how to really introduce a chiral gauge theory. So people are working on it and trying to make some progress, but it's not yet done. It's formalism-wise, it's not known yet.